As I tried to preview earlier, this will be the second presentation by Doug, offering kind of an answer to the disruptive technology he mentioned earlier, specifically the NVM programming model. Those of you who are familiar with the InfiniBand spec and verbs will find, I think, some very interesting parallels in terms of how this programming model is pulled together. Doug?
Thank you. Okay, you guys remember this. It was only half an hour ago. Things are getting faster. Okay, so what we're basically proposing in SNIA when it comes down to the persistent memory model is a memory map files approach. So I'll elaborate on that a bit, but there's the spoiler, right? We've been working for a little over a year on version 1. It began sometime in 2012, work on it. And late last year, it went out for vote. So it's now a SNIA architecture. So the spec deals with both block and file, traditional block and file, as well as persistent memory. There are new aspects of block standards that are not yet uniformly accessible to applications. So we dedicated some of the spec to kind of calling those out and suggesting a systematic way of exposing some of those, such as atomicity and thin provisioning management to applications. So that's one part of the spec. And then another part of the spec, and I'll elaborate on the distinction again, is where you're actually doing memory map files. And we felt like, first of all, this is an existing method that is actually made more powerful by the notion that the memory could actually be durable. So that the point came up earlier about sync. Well, in this spec, basically we would use the map and sync API calls or analogs of those to actually do the sync and ensure that the CPU's caches, volatile caches and so forth are all flushed out to what we've called the persistence domain so that they're durable. So instead of the traditional version of sync that does disk I/O to get data out of volatile memory to disk, what the sync in an NVM programming model persistent memory mode would do is simply flush the CPU's caches so that the data is in persistent memory. That way, so we surround that with a file system so that we don't have to reinvent any more of the system than necessary. The idea is that you would need some sort of namespace construct and some sort of access control construct, anyway, in order to build up essentially a storage system in memory. So he said, why not use basically the already existing file system paradigm for that? And we've found that you can actually build a lot of other things on top of that, without much loss, because once you have something memory mapped, you can basically access it directly. Another thing that kind of resonates with some things I heard this morning is that we chose to describe a programming model and not an API. It's more like a verbs type description, but we tried to stay at a fairly abstract level, at the application level, looking like a volume or a file system. We used actions to describe the things you can do and attributes to determine what a given system's capable of. And we use use cases in the specification to describe how we expected the specification to be used, or the actions and attributes to be used. I guess one of the things that we had to confront immediately is that this will involve the kernel, and for most of our businesses, that means it might be Linux, or it might be Windows, or it might be VMware. And we don't expect Linux and Windows to agree on an API. So specifying a programming model, seemed to be the best way to get a pervasive behavior across a wide ecosystem of components in the industry, while being able to access them from sort of native APIs of each operating system or native file system, using the software that assumes the behavior, the underlying behavior of the devices that's described in the spec. So it's a classic case for a programming model. The conventional block and file modes look like this. There's not really a lot of new stuff in this part, in this mode. There are atomic multi-write features being introduced through the SNIA standards groups, and I think there's some of that in NVMe as well. For atomicity, we want to be able to express granularities, and some of the thin provisioning management has not been uniformly exposed to applications. So we've been trying to call that out and get some alignment, around basically how do you take those lower level things and expose them to applications in a fairly uniform way. And similarly with file systems, right? There's currently no standard way of looking at the atomic write and granularities and things like that through your file system. So that's what part of the spec is about. The other part deals with persistent memory, and I think this is probably a review. And when we talk about persistent memory, we mean specifically that it's byte addressable with load and store instructions, and it has memory-like performance, meaning that this is the scenario. I think this would be M-type, as per the previous presentation, where the CPU actually does stall while waiting for the access. So that means that for us, persistent memory is fast enough to make it reasonable to stall the CPU, during the memory access. And we believe that some of those technologies are getting into that range, and in fact, some of the numbers in the previous presentation, were in that kind of NUMA, latency range, and that it's DMA-able. Including that we want to be able to do RDMA to persistent memory directly when it's not on a memory bus. Well, not on the local memory bus, right, where it has to go over a longer distance network of some sort that's not a memory fabric. It's not prone to unexpected latencies, and what we're really trying to drive home here is the notion that when you memory map something, you expect it to stay in memory and have memory performance. There are a lot of schemes that can do basically demand paging or, based on the virtual memory system, cause page faults and use the memory more creatively. But the thesis here is that if you've memory mapped something, then you actually expect it to be in memory, and that over time, the cost of the technologies that are memory speed will come down to a point where you can have a very large amount of persistent memory operating at memory speed inside a server. So we're looking forward to that day when it's actually feasible to basically view your persistent memory as if it were your primary storage. And of course, you want to not have to go through page cache, for example, when you're doing Linux file accesses. So there's an emerging, actually already existent for a long time, right, analog to this, which is battery-backed RAM. So it basically that's a perfectly reasonable model for what we're talking about. And we think there'll be more and more cost-effective ways of doing that over time. So here are the persistent memory modes called out by the spec. You have a driver element still that is capable of controlling the persistent memory devices and configuring them so that they can be directly accessed. But the driver is intended to be out of the access path in these persistent memory modes. And then the persistent memory aware file system, which once you memory map something, uses this direct path that's all the way over on the right through between the gray boxes, and that's what represents. I don't have an angle on this. The load store access. So once you open the file and memory map it, then you're really talking directly to the persistent memory. The volume mode is present to expose ranges of memory that represent the equivalent of a volume to kernel modules. And some of those could be the file system itself or other types of modules that want to consume persistent memory in a more raw form. So you end up with a list of physical address ranges that represent a volume. And then if there is thin provisioning implemented, then that's also part of the interface here. In the file mode, it's basically a map and sync model. And then during the sync, as I pointed out before, we mainly have to do the CPU flushing to make sure that the data is made it to the persistence domain. As we start to get creative and get back into, perhaps offering some high availability features or actually adding value in this direct access stack, the interesting question becomes, what happens to the sync, right? It could be that the sync or some variation on a sync is the point where you want the data to be both durable and fault tolerant. So it could be that during the sync, or perhaps through some aggregation process across a number of syncs, you start to engage an RDMA protocol in order to get the data to a distant system that's not necessarily in the same memory fabric as the local system. All right, so that's where the RDMA use case starts to come in. I'll talk about that some more in a minute. So as I pointed out, kernel modules may use the volume mode, PM-aware file systems, other storage stack components. For example, the previous presenter talked about exposing a block mode. That's the same sort of thing we're talking about here. Oops. This thing is still a little tricky. You might use the NVM PM volume to say, okay, give me the ranges of persistent memory in this volume so that I can present a block access model to those ranges, right? That would be an example of this storage stack component, and that's the same thing that we were talking about in the last presentation. The PM file is for use by applications in normal persistent data sets, perhaps also as caches. The advantage here, of course, is that you get the warm cache effect from having your system come up from power loss with basically its caching intact. Or if you're using it as just plain primary storage, then obviously it's got to have those attributes of primary storage. Or more abstract, blobs of persistence, where you can use the file as an underlying abstraction, which gets out of the way very quickly, and then you can build other types of abstractions on top of the memory mapped file once the whole file system is out of the way. But it is up to that point, it's already given you a naming and a permissions model, so that you can really treat your persistent memory as storage. Having released version 1, we're now starting to work on three additions to the spec. One of them has to do with software hints, and this is where some of what I was talking about in my earlier presentation. What kinds of attributes should applications be able to see regarding their storage? Are there useful access patterns that should be surfaced from the application downwards? Are there optimizations that should be triggered by upward communication? And various hints that are emerging in the standards already in both SCSI and NVMe are sort of precursors to some of this. We are also considering a type of atomic but more transactional behavior. There are a number of ways to do atomics, and we're looking really in the direction of not the individual primitives for atomicity, but more of a roll forward, roll back transaction type construct. Because we found that with just the sync, it's not very efficient to get a very useful recoverability proposition. You need something a little more transactional. So if we can present a transactional mode to applications, then we should be able to optimize that more effectively than you could do if you only had sync exposed to applications. So I think that is probably a pretty natural line of reasoning for this group. And then remote access. I already mentioned the disaggregated memory mode, but we think it's important to be able to do RDMA direct to NVM when the NVM is not in the same memory fabric. And one of the, there are several use cases for that, including the ones listed here. Most notably, the high availability use case. And that's where I think our two groups' agendas overlap once again. So we'd like to be able to use RDMA let's picture it like a sync, except that it's got to do not only durability but fault tolerance. And the application is envisioning the thing as being something close to memory speed, something that was similar to flushing caches, right? But now it needs to somehow efficiently get the data off to a different fault domain, probably through some sort of RDMA copy for high availability on memory map files, as an extension to the model that we've already worked on. One of the things that we need in order to do that is to know as efficiently as possible when the data that we've RDMA'd is in fact durable at the remote location. Now, I'm sure there are ways to do this with additional passes, round trips over the network, all right? But what we're looking for is something as efficient as possible as a way to do this, keeping in mind that in general, currently, these interfaces, RDMA interfaces all come through PCI, which comes through the processor, and who knows what volatile caching the processor might, well, someone knows. The processor might be doing on the way to memory. So, is there some way, what's the most efficient way to use RDMA in such a way that the source can be confident as to when the remote copy is in fact persistent, has made it all the way to memory, regardless of whatever buffering is happening in the components along the way. So that's one of the challenges, which I've started to list down here in the requirements category. A second is efficient byte range access, and I've seen several things this morning already that have already been happening. Some in the message passing, perhaps in the put and get domain, that may get at this. You got to picture the use cases that an application has modified some number of cache lines in memory as manipulating its variables, and then it does a sync, what it wants is for those cache lines basically to become durable, and in this use case also highly available. So you end up with a lot of little fragments, right? So does that call for some sort of scatter-gather RDMA? What is the most efficient model that we could use that starts to approach, that expectation of memory speed with maybe a sort of flush penalty and a little bit more HA penalty, to actually get this type of communication to a different fault domain? Then there's the question of addressing. Let's see. I think we've already talked about scenarios where there's a uniform virtual address space. The interesting thing that happens with persistent memory map files, especially when you're viewing them as essentially your primary storage, is if you have pointers and data structures that are in memory map files, they're probably virtual addresses of something. What form should they take? Can you account on getting mapped to the same location, after a power fail? What's is it a base displacement style of addressing? Is there some way to perhaps couple this kind of more persistent, more stable, persistent storage addressing mode with the way RDMA is done. So that's kind of a wide open question, but what it leads back to, I think, is if you're going to do something like that efficiently, maybe there's some way to do late binding without a connection teardown, and that brings me right back to that direct, or what is it, DC mode that one of the presenters this morning was talking about, and a question of how efficient is that? All right, so I'm already starting to see some discussion here that kind of gets at some of these requirements, and perhaps in different ways than the way I've asked the question, but still ways that could be considered as efficient ways of achieving fault tolerance for persistent memory. Often today, when people do RDMA, they as Microsoft, for example, in SMB does RDMA. They always do it from the server and pull the data from the client to the server. That's for security reasons. Can we set something up when you're doing high availability memory map files, that is secure and yet only does one pass, right, through the network, and perhaps aggregates responses, over a series of sinks or something like that, so that you get a really efficient protocol for doing high availability memory map files. And then the question of recovering resources and fencing hardware after failure. If you've got an RDMA connection set up and you get a failure, you have to be able to ensure that all the resources involved were recovered and that you get the emulated fail-stop behavior that we all kind of count on but don't always get, perhaps through some sort of fencing. So those are considerations when you're talking about the high availability model. So this is an area that we've just started exploring, and there's a lot more RDMA expertise in this room. Probably any one of you has more expertise in RDMA than the twig does, right? We haven't been immersed in that. So that's an obvious area, I think, for collaboration and brainstorming as to how some of these things might be efficiently done. So wrapping up, we're at least trying to align the industry around a model for persistent memory so that we can build that sort of architectural hourglass, in the form of a programming model that operating systems can pervasively implement, and that storage and memory vendors can likewise, implement on the hardware side. So that's really what we're after, and to really kind of drive the acceptance of persistent memory into the mainstream over a period of time by, encouraging application adoption. Without using specific APIs, it is a programming model, and then there's the URL for version 1 of the spec. We're exposing it through some open source implementations. One specifically is at this link on GitHub, the PMFS implementation. And we've got some examples such as persistent memory alloc that's listed here at this next URL down here, that's also built on top of our persistent memory model. And we're convinced that as emerging technologies drive the cost of persistent memory down, this stuff will become more mainstream, and we'll be looking for this kind of programming model standardization in order to really drive the ecosystem. So that's what we're up to. How'd I do? Questions?
Just a simple question. How big are your addresses?
Let's see. So we don't say, right? It's, what's that?
128 bits? 256 bits?
It depends on what on which addressing model you assume, right? If there's a camp that's more of a base displacement addressing model, in which case you may not have to have as expansive an address. But if everything in the universe has a virtual address, then 64-bit probably isn't enough. All right, so yeah, but the level of abstraction we're at here doesn't really deal with the question of that type of address. So that would be something that has to enter with the specific API. Okay, thank you.